Good morning everyone. I am Yogesh Poul. Today we are going to discuss about polynomials in lattice. So the set Pn of n array lattice such that xi belongs to Pn where all I 1 I is equals to 1, 2, 3 up to n minus 1
I is equal to 0 from I starting from 0 x naught.
x naught.
Ah.
Yes. P comma q belongs to Pn. It implies that P or Q belongs to Pn and P and Q, so P join P meet Q belongs to Pn. Let us we take an example of a polynomials in lattice. Let's suppose n equals to 3.
1 second. First, try to understand what is that meaning.
Yes.
What is that set of P of n denotes? They are basically n array lattice
It is
polynomials
yes.
where all monomials are there. X naught is there, x1 is there. All those things should be there. And if you take any two polynomials there, P comma Q,
Belongs
then its joint should be there and mid
mid
should
should
be
be
there.
there. Okay.
Then we say that that is the set P of n. Is that clear?
Yes. Let us suppose n equals to 3. Then we have three variables x0, x1, x2. Share polynomial P x0 join x1 join x2. This is a P is a polynomial of three variables x0, x1, x2.
This is one example.
Yes.
You can give lot of examples. Can you give
Yes.
someone can give some example of polynomial?
Yes. x0 meet x2.
You can take combination of meet and
Yes.
join also. Okay. Not only meet will be there, only join will be there.
Can we take another example of this?
Even just x naught is also a polynomial. Yes or no? Even it is not necessary that every time three variables should be involved. Even one variable is also sufficient. Yes? No, n means number of variables. Here, for example, n is equal to 3. So, I suppose for n is equal to 3, how many variables will get? X naught, x1 and x2, 3 variables. Right?
We can take also another example of this. If we take n equals to 4,
Say it loud, your voice is little.
if we take n equals to 4, then the variables are x0, x1, x2 and x3. Here p equals to x0 union x2, p join x0 join x2 meet
Even you can write x2, write x2,
x2.
join x naught.
Yes.
See, it is like x2 is you write different one. X instead of x0 you write x1 there. Last one, x1. So they can repeat also. Okay, it is not like only one time that variable should come. It is not necessary. Is that clear?
Now we discuss about a polynomial function.
So whatever we have defined in that P of n, they are all polynomials. Actually, they are functions. Means how it look like. So when you say a function f of x, so you can substitute the value of x there. Is that clear?
A polynomial function we satisfying the following properties. First one,
Right? Fast.
here x0, x1, x2. This is a n-ary polynomial. Then this is our first property.
Wait. What is meaning of this? For example, if your polynomial is a monomial in one variable, means if this polynomial, even though it is defined in n variables, suppose if it is just some xi, then what should be the value of when you substitute some number? It is simply that particular coordinate ai. Is this clear? That is usually naturally expected. So polynomial should satisfy that condition. Are you following?
Let us take the second property. If p equals to a0, a1, a2 up to an minus 1 and q equals to
That is not p equal to, it is p of p evaluated at a naught. You remove that equal symbol. It is p of a naught a1 up to a n minus 1. If suppose that value is a, and p of next one is q, right? Next is q. Suppose q evaluated at that point the value is b, then
and r equals to p and q and t equals to p join q and t equals to p join q. Then we write r as
r. What should be the answer? You all can tell. What should the value? It should be a meet b. Yes or no? And t evaluated at that point is a join. Is that clear? So this is already we know in regular polynomial. Suppose you take one polynomial and another polynomial, you add them and evaluate is same as you evaluate and add them. So similarly here you are finding p at that point, q at that point, then you are taking meet. Is this clear? So a regular polynomial, what properties it satisfies? Here also it should satisfy same thing. Yes, next.
Let us take example. If n equals to 3, then the variables are x0, x1, x2. Here p of x0, x1, x2, let's say x0 union x2 and
x1, middle one is x1. Huh? What you are calculating?
p of ABC.
Okay, so what
Then
is value of P of ABC? You all can tell what is P of ABC? Huh? A join? Tell properly. A join? A join B. How A join B? It is X naught join X, right? A join C. Huh? A join C. C. What is B meet C?
R of ABC.
Suppose you define what is R. You write above step R is equal to P meter join. What you are calculating? What is your R? Okay. Say suppose.
Here R is equals to P meet Q and T equals to P join Q.
Okay.
Then R of ABC. What is R of ABC?
It is P evaluated ABC and Q evaluated ABC, right?
Then T of
Now first tell me what is that value. Can somebody tell what is this? You can simplify this. Huh. B meets C. Very good. It is B meets C. Why? Because this A join C is bigger than B
B
meets
meet
C.
C.
So meet will be smaller one. Yes or no? So answer is B meets C. Right
Here,
there equal to B meets C.
here R of ABC, A join C, meet B meet C. Here B meet C is smaller than A meet C, A join C. So here B meet C.
Yes.
Here T of A B C. What is the T of ABC?
It is join of ABC.
T of ABC is a P or P join Q. What is the value of T of ABC?
Why it is A join C? Whether everybody understood? Because A join C is bigger and B meets C is already there inside. Yes?
Rank of a polynomial. Uh, Here rank of P join Q is equals to rank of P meet Q is equals to rank of P plus rank of Q. How to find the rank of Q? Here if you have a rank of a single element monomial xi, then its rank is a 1. If you take a in a variable, let us take an example. If here if you have one variable, one monomial, then we take a its rank is a 1. Here what is the rank of P? Yes.
Suppose you write Q is equal to x naught join x2, x join x2 meet meet with x naught. Now, what is the rank of this polynomial Q?
According to this definition, rank of P join Q, rank of P is equals to rank of P meet Q, then is also equals to rank of P plus rank of Q.
So it should be 3, right?
Yes.
Yes or no? So it is not like x1 is repeated 2 times, so we have to count only 1 time. So how we can understand rank? The number of variables with multiplicity. Is that clear? For example, here x0 and x2, but x0 is repeated 2 times. So x0 repeated 2 times and x2 is involved, so rank is 3. Is that clear? And you are not supposed to simplify that expression. Even x0 join x0 is not simply x0. It is actually x0 join x0 only. Is that clear? Because it is a polynomial. When you substitute some value, you get the simplified value. Are you following? It is just like in a polynomial you have x plus x. It is just like 2x. You can't say x plus x is simply 1x. Is that clear? So if x0, x1, x3 or anything, they can be repeated n number of times. So that you cannot count as only one time. So basically rank means what? Number of variables involved with multiplicity. Multiplicity is important. Is this clear? Yes.
Let us take another example of a polynomial. If you take a P equals to x0 join x2 meet x1 meet x3,
So obviously, what is the rank? Everyone can tell
what should
now.
be the rank of this?
4.
Yes, because of we can write this rank of P plus rank of Q. We can further describe it. Rank of x0 plus rank of x2 plus rank of x1 plus rank of x3.
So basically, you are going to split, 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 and finally you are going to monomial. And rank of monomial is 1. Is that clear?
See, rank of x2 x0 1 plus rank of x2 1 1 plus 1. So what is the rank of this? Yes.
What is meant by constant here? Hmm? So if there are no variables are involved, rank is 0. Number of, if you x0, x1 up to xn minus 1, if nothing is involved, then it is a, if you say it is a constant polynomial, then rank is 0. Okay. What? Maximum? Why? It can be anything. X0, 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 you keep on repeating, na? What is the problem? N is number of variables. N is number of variables. See, suppose if you take N is 3, that means variables are x0, x1, x2. But these things I can take 2 more times. So rank can be 6 also. Okay.
Now here is one theorem.
Right, fast.
Let H be a subset of latticeal then if
A is equal to H use symbols H not H1. Explain that statement again. What this statement says?
let H be a subset of a lattice L, then A belongs to H. What is H? H is the smallest lattice,
No, that is a
smallest
square bracket H, right? Huh.
smallest sublattice
Huh.
generated by H.
It is the smallest sublattice, okay, uh, containing H. Okay, containing H. That means if you have any lattice containing sublattice containing H, then this is contained there because it is the smallest. This is smallest among all sublattices containing the set H. Is that clear? One second. So what it says is that so some element will be there in that sublattice if and only if A can be A is a value of some polynomial. Is this clear? And those HIs are coming from H. But we know polynomial means what? That right hand side, it is either meet or join of HIs. Yes or no? That means A will be there in H, square bracket H, if and only if A is combination of elements of that H with meet and join. Is this clear? So any A can be written as me HIs meet and join. Is this clear? Then we say that A is there. It is just like A should be generated by elements of H. Here generated means using meet and join. So A will be there in H if and only if A can be written as elements of H with join and meet operations. Is this clear? That is the main idea of statement of that one. Yes.
Consider Hn minus 1 our claim is that S is a sublattice.
So the idea of proof is we want to prove that A belongs to H if and only if A satisfies this condition. So whatever we are having that we will collect as a set S. So S contains that type of thing. Then we will show that S is a sublattice and which is basically equal to that square bracket H. Is this clear? Yes or no? If we show that S is equal to square bracket of H, then we are done or not? Yes? Because any element in S is of this form, and if we show that it is same as square bracket H, we are done. Are you following? So to show that S is equal to square bracket H, show that it is a sublattice and that is equal to H, right? No, you don't require any uniqueness. है ना? So we will show that S is equal to that square bracket H, means one is contained in the other. Suppose if we show this last one, H is contained in S and S is contained in H, and if we prove that S is a sublattice, then what we will know? This is a sublattice containing H, yes or no? And we will prove that it is also contained in that square bracket H. But what is definition of square bracket H? Because it is the smallest subset, sublattice containing H, so therefore square bracket of H will be contained in S, so they will become equal. Is this clear? Yes.
Clearly, H is a subset of a S.
Why it is H is subset of S? That means why every element of H is in S? Why? Can you represent every element of H as value of some polynomial? What is that required polynomial? Right, small h belongs to H. So right, H is equal to small h is equal to P of something. Can you tell now P of something? Don't write now. I want from you. What polynomial we can take so that P of that value is actually H? Huh? You don't go to join and all. When you substitute some value, you should get that same value. So what is that polynomial? Identity. Very good. Is that clear? So you take simply P of polynomial as identity polynomial. Are you following? So simply take P of any xi is equal to xi. Is this clear? P of x is equal to x, right? P of x is equal to x. It is a identity polynomial, yes or no? Then for any h belongs to h, what is P of h? P of h, P of small h is equal to h. That means your h is value evaluated of the polynomial P of x. Is that clear? That shows that h belongs to s, small h belongs to, is that clear? Small h so belongs to. Are you right? Capital H is contained. H
Small h belongs to S.
belongs to capital S. That proves that H is contained in S. So as I said, clearly usually doesn't follow immediately. One should understand that concept, right? It is usually easy, but we only skip. Clearly means we skip, but it is not like that. Don't write anything. To show that S subset of S is contained in S. No. S is contained in square bracket H, right? How when we will show that one subset is one is contained in the other? Take one element there and show that that element is there. So let A belongs to S. What is the meaning of that? When some element is in set S. Where is your set S?
Sure. here S is a
Huh.
A says that A is equals to P of H1, H0, H1 up to
A is a
Hn
value of
minus.
some polynomial. Yes or no?
Yes.
Right there. So there exists H0, H2, Hn minus 1 in H square bracket, round bracket, not flower. Huh? Huh. A is P of that value. Where are HI's?
HI
HI's are
belongs
in
to
capital
H.
X. Yes? Yes. Now we will prove this one by help of rank of that polynomial P. What is rank of that polynomial? Using that we will prove that A will be there in bracket H.
समझ में नहीं आ रहा सर समझ में नहीं आ रहा सर
See, suppose rank of P is 1, right? Suppose just SUPP. Suppose rank of P is 1. What is meaning of rank of P is 1? It is a monomial. Okay? Yes or no?
yes
That means P of x naught up to xn minus 1 is some xi. Right? P of x naught comma x1 up to xn minus 1 is equal to xi.
XI
ठीक है, P is equal to xi. Therefore, what is P of h naught, h2, hn minus 1 at that time?
अच्छा
That hi. Yes or no? Therefore, P is P of h naught, h1 up to hn minus 1 is equal to hi. Is that clear? That is our A. Is this clear? But hi belongs to where? Capital H. That means our A belongs to capital H or not? Because our A is P of that value. This implies A belongs to H. ऊपर लिखो थोड़ा, next इधर लिखो. A belongs to H. Right? If A belongs to H, can we guarantee that it is there in square bracket H? Very good. It's because H is contained in square bracket of H. Is that clear? As H is contained in, as H is contained in capital H is contained subset square bracket of H implies what we will get, small a belongs to square bracket H. Is that clear? We proved that A belongs to H, so therefore A belongs to square bracket. So if rank of P is 1, we are done. Now we will assume, means we will prove by mathematical induction. So assume that if rank of P is less than or equal to say K, then this should be true. Is this clear? Any polynomial. If rank of polynomial is less than or equal to K, at that time, if A is equal to P of that values, then it should belongs to square bracket of H. Yes. You write there A belongs to H means A is equal to P of that value. Otherwise, what is relation between A and P? A is equal to P of H naught up to Hn minus 1. Is that clear? So this, understand properly, our assumption is if we have a polynomial whose rank is less than or equal to K, and if A is the value of that polynomial, then A belongs to square bracket of H. This is known to us. Is this clear? I mean, we are assuming, and we want to prove what? Now let rank of polynomial is K plus 1. Rank of P k plus 1. For this also, if A is equal to P of that one, we want to show that A belongs to square bracket of H. Is this clear? Why? What is meaning of this one? Because rank of P is k plus 1. That means at least there are exactly k plus 1 in variables are there with multiplicity. Yes or no? Just a second, 1 second. Wait. So we can write this as combination of two polynomials. It may be join meet. Is this clear? In such a way that both polynomials rank is less than or equal to k. Is this clear? Yes or no? That is always possible, because if you write as join or meet, and if both rank is greater than, strictly greater than k, then the rank of p is not k plus 1. Yes or no? So where rank of R and rank of T less than or equal to K. Yes or no? Simply write R of K. Okay, rank of R. Rank of R. R and T are polynomials, huh? Is
Then
K नहीं रहे उधर, rank of R of R. K कहाँ से आ गई? अरे वो नहीं.
R of
इधर starting where के बाद R of, हाँ K नहीं है वो R. वो polynomial R है. हाँ. It is not B, right? It is not A. It is some value B. B or C.
this.
Say some B. Is that clear? So what we are applying mathematical induction for R and polynomial R and T, because their rank is less than or equal to K. When you substitute HIs, whatever B and C, where are they? You write there B belongs to where? Just a second. B belongs to, by assumption, what we know? B belongs to square bracket H. Is that clear? B belongs to, similarly C also belongs to square bracket H. Is this clear?
Then what is P? P is a meet or
P of H naught H1 Hn minus 1. Right? P.
yes.
P of H naught is equal to either, what is that value? Either it is B meet C or B join C. Is this clear? But that is our A. P of H naught Hn minus 1 is our A. Is that clear? Right there equal to, na? You write there as A. Okay. But B and C are in H, square bracket H, but it is a sublattice. So what is meaning of sublattice? If two elements are there, no, their meet and join will be there. Sublattice means it should be closed with respect to meet and join. So B join C, comma B meet C belongs to square bracket H, right there. B join C, comma B meet C belongs to square bracket H. Is that clear? But our A will be any one of this one. This implies small a. A belongs to square bracket H. Is proof clear? So obviously what we did is, because rank of polynomial, if it is k plus 1, we will try to write that polynomial as combination of two polynomials whose rank is less than or equal to k, and apply the mathematical induction hypothesis. Is this clear? And because square bracket H is already a sublattice, If two elements are there, then their join and meet will be there. Is this clear? So from that we prove that A belongs to H, right? Square bracket H. That shows that S is contained. Therefore, right there. Therefore, S is contained in subset notation. Square bracket H. Is this clear? Now from this, tell me why S is equal to square bracket of H. Hmm. Hmm. So square bracket of H is the smallest sublattice containing H. We already proved that S. We are yet to prove it is sublattice. We will prove that. But suppose assume that S is a sublattice, and it is already containing H. Yes or no? Right?
Now we have to prove S is a sublattice.
So once we prove that S is a sublattice, our proof is concluded. S will become square bracket H. Is this clear?
Here.
What is meaning of proving something is a sublattice? Take two elements and prove that meet and join of those two elements are there. You write there, don't take tension, let it claim. You write S is sublattice, there you write claim. This we are proving, just this we are proving, so you write here it is a claim, so that understand. To prove it is a sublattice, let A comma B belongs to yes.
Yes.
Then by definition S, how it is defined? A is some polynomial evaluated at some points. Similarly, B is value of some polynomial evaluated at some points of. So here HI's are in H. This need not be N, it can be M. Similarly, HI primes are in H. Is this clear? Now somehow we want to show that A meet B, A join B also belongs to S. Is this clear? That means what? This should be the value of some polynomial evaluated at HI's. Similarly, this should be the value of some polynomial, right? So we want to find some suitable polynomials. That is the, to show this, we want to find suitable polynomials and substitute those values, right? H naught prime. H m minus 1 prime, m, that is m. It is not necessarily be H n minus 1, m minus 1 prime. Just a second. Class should not be this much silent. The idea is we have polynomial p in n minus 1 variable, q in m minus 1 variables. Okay. Now we are going to, when you talk about meet and join, so you should have a polynomial involving those variables. Yes or no? So we will define new polynomial p prime. P prime in this n minus 1, n plus m variables. Are you following? N plus m variables. Some may be different also, some may be same, then you can skip that. Is this clear? How you define this? You define using that p value. Is that clear? See, it is just like you write p of x comma y as simply x, even though it is defined in two variables, but that value is always x. Is that clear? So here we will define p prime of these many variables, but actually it takes only first n minus 1 variable. Are you following? Say something why you are writing. Huh? At least this you can say, na, you are taking p prime and q prime.
Yes.
Okay, in more variables in such a way that p prime, when you substitute this hi values, it is same as p of that values, p of hi values. Similarly, q prime of these values is same as q of h naught prime. H naught prime, you write h naught prime, h1 prime up to hm minus 1 prime. Is this clear? So therefore, now what is that p value is a and this q value is b. So r of this value, r of h naught up to hm minus 1 prime is a meet b. Is this clear? R is a polynomial or not? R is a polynomial in at most n plus m variables, right? Prime hm minus 1 prime, that is equal to, it is same as what?
This is the meet of this.
Because we have
Meet
defined
of
it as,
this and this.
we have defined r as what? P prime meet q prime. So r of that value is evaluated, p prime evaluated that value, q prime evaluated that value, which is same as, which is equal to, don't write again and again, which is equal to, what is p prime evaluated at that, this one, yes or no? There only you write, 1 second, there you write equal to, you write that is equal to a, yes, then this one next one is b, yes or no? So therefore that is equal to a meet b. Okay, write fast. We should not waste too much time in writing. This is same as what? A meet B. Yes or no? So what we have concluded, A meet B is the value of the polynomial R. Okay, evaluate at the points h naught up to hm minus 1 prime. Is this clear? Therefore A meet B. Therefore A meet B belongs to S. You write A meet B. Yes. Is this clear? We are able to write A meet B as a value of some polynomial evaluated at those hi's. Is this clear? Similarly, you can prove for join. Join also same. That shows that this implies S is a sublattice. Implies S is a sublattice. मैं बोलना ज़्यादा हो गया, आप बोलो ना. So far what we have proved, just a second. So far what we have proved, we proved that S is a sublattice and H is contained in S. S is a sublattice containing H, and what we know about square bracket of H? By using these two, what we'll get is, because it is the, by definition, it is the smallest sublattice containing H, means it should be there. Is this clear? But we are, what we have already proved that S is subset of H. So if you combine these two, what we'll get? This implies S is equal to this. And S is precisely those elements whose are values of polynomials. Is that clear? So that proves the theorem. Is that clear?